If you're with me in class, then you'll be filling in some notes as we go through these problems. The first 4 questions, I hope you've already tried those on your own. Let's check to see how you did. We're setting up our difference quotient definitions for the derivative at 2. So first, let's use our definition, the limit as h goes to 0 of f of x plus h minus f of x all over h. And here notice that we are letting x become 2. So everywhere in that definition where we see an x, we're now going to make it a 2. So let's take a little detour here. This is going to become an f of 2. So let's do a little bit of arithmetic here. F of 2, simply putting it into our function, will be 2 squared plus 3 times 2. So our f of 2 we can just turn into the number 10. All right, so let's see what we can do here when we replace. So now we're finding f prime of 2. So our f of x plus h term is going to become a 2 plus h. So into the variables of our function, we are going to put 2 plus h. So there's our first, that's our f of x plus h term. And then minus our f of 2 term is already done. We've got a 10 over h. So there's our first definition. And now let's use our second definition of derivative. F prime of a is the limit as x goes to a. Of course, you can use whatever variables you want here. So we want the difference of the function over the difference of the x coordinates. So there's our limit of a slope. And this time, our a is going to be replaced with a 2. So this is the limit as x goes to 2. And our f of x, our function, stays as it is originally written, x squared plus 3x. And then minus our f of 2. So our f of 2 was 10. And down here, remember that our a is our value 2. And of course, you could do the algebra and find that derivative. All right, so we know we could have done that quicker, though, with the power rule. Let's try another one. We're practicing our definition of derivatives here. So our f prime, this time our value is 4. So our f prime of 4 is going to be our function at x plus h. And our x value is 4 minus our f of 4 value. Maybe let's, since we're going to use it twice, let's make sure everybody sees what we're doing here. 4 squared is 16 plus 11 is 27, which is a perfect cube. So we will get our f of 4 value is a 3, all divided by h. And then let's use our other definition, our f prime of 4. Oops, up here I forgot. That would be a horrible mistake. That would be the slope of a secant. So remember, to make it the slope of the tangent line, we need to have that limit there as h goes to 0. All right, and then for our second definition, we're going to have the limit as x approaches a, and our a value this time is 4. So we have our f of x function, no change at all, except of course that our x value is 4. Whoops, nope, not yet. That's our a value in this case. Our f of x, I'm jumping the gun, our f of x term minus our f of a term. So our f of a term is the one that got replaced there. All divided by x minus a. So our a term is our value 4. All right, do we recognize the shortcut then? Well, do you see that this term right here is our f of x plus h, so it looks like our function must be x cubed, and you can check that out here. We believe that our function is x cubed, and what are we putting in for the h value? We're putting in 5. Does it check out that f of 5 would be 125? And it would. So what we're really saying here is that for f of x equals x cubed, we are finding f prime at 5? Well, we know by the power rule, shortcut, that f prime is 3x squared. So we would be able to quickly come up with the answer, 75. I think we've done that problem before. Here, this part would be our f of a. So we're switching to the other one because I don't see an h. That's how I knew we were switching. So there's our x approaches a term, so I know that a is 25. So this 30 must be our f of 25. So what's our hypothesis here that our function is? Our function must be the square root of x plus x. So the derivative would be 1 over 2 square root of x, use the power rule, plus 1. And then our f prime of 30, let's check it out, our f prime of 25. If we have 25 here, square root of 25 will be a 5, so we'll get 1/10 plus 1. So our shortcut, we should come up with a 1.1 or an 11/10. All right? So remember why this is 30, by the way? This is 30 because if we put 25 into the function, do you see why? If we put 25 into this function, do you see where the 30 came from? So 5 plus 25 is where that 30 arrived. So, all right, so we'll have to keep practicing those throughout the year. If you're watching this video in Edpuzzle, then, and I think I noticed perhaps I have a problem here with my symbols. Let me pause and double check. It looks like I got a typing mistake here. And indeed, I did have a typing error there, so we've got to make our answers for the multiple choice question match. So if we asked you to evaluate this limit, so choose your answer, and then you're going to enter A, B, C, or D into the Edpuzzle if you're using the Edpuzzle format. I'll pause and be back with the answer. This would indeed be the sine function, and we are asked to find f prime of p. So it would be cosine of p. The derivative of sine is cosine, so I think letter A looks correct. All right, now we're going to take some notes and summarize a lot of what we've already been discussing about derivatives. So very quickly, we'll fill in a number of these. We know the derivative of a constant function is 0. Keep in mind that a constant function is a horizontal line. So f of x equals 7 is a horizontal line, so of course its derivative is 0 everywhere. If we have a slope-intercept form equation, of course we know that the slope is m, so we know that the y-intercept is b, and we know the slope of this line is always m, so the derivative is m. So the derivative here, and it checks out using our power rule, the derivative of 7x is 7, and the derivative of -1 is 0. So the power rule works fine. Writing our power rule, we would have n times x to the n minus 1 power. So the example here, we would multiply the 2 times the -3, and we subtract 1 from the exponent. So whether you write it with a negative exponent or whether you prefer to move that x to the 4th denominator to the denominator is your choice. All right, what if we are multiplying a function times some constant? Well, we can do the constant outside of the derivative. So here's the example that we're talking about. The derivative of 2 times a glob. We can simply do the derivative first, and then we can multiply it by 2. So do the derivative of your function and then just double it later. All right, some of these trig derivatives, we need to learn more formulas in order to prove these, but I want to make sure that you're starting your list of derivatives that you have to memorize, and then we'll also check to prove where these come from. So we've already done these first two. Remember, the derivative of cosine is negative sine. The derivative of tangent, and you'll see why in a few short days, the derivative of tangent is secant squared x. So the matching formula should have something to do with cosecant squared x. And the mnemonic that helps you remember these is the derivative of all of the co-functions starts with an opposite. So the derivative of cotangent is the opposite of cosecant squared. Secant and cosecant might be the toughest for students to remember because they are products. The derivative of secant is secant tangent. Secant times tangent. So the derivative of cosecant, likewise, is cosecant times cotangent. And then you'll remember that it's a co, starts with a co, so it has to have an opposite in front of its derivative. So start working on your memory there. All right, so we'll see what you can do if you try answering the question. What is the derivative of cosecant x minus cosine x? Remember that the derivative of a difference is the difference of the derivatives. So simply do the derivative of each term and then pick your answer in Edpuzzle. And we're back. The derivative of cosecant, we found out was negative cosecant x cotangent x, and the derivative of cosine is negative sine x. So these subtracting a negative, I think, would give us choice A. Hopefully that's the one you picked if you're watching this video in Edpuzzle. All right, some more terms that you're going to remember. We've already seen briefly that the derivative of e to the x is still e to the x, a unique function in calculus. The derivative if a is any other constant. So a is a constant. And it turns out that the derivative is a to the x times the natural log of a. So if we have the derivative of 7 to the x, here's an example of that. The derivative is 7 to the x times the natural log of 7. All right, the derivative of the natural log is 1 over x. And we'll discuss later with and without the absolute value. You would get the same derivative there. The derivative of a logarithm in some base other than e, so not a natural log, you will get 1 over x times the natural log of the base. So here's our example. The derivative of the log of x in base 7 is 1 over x times the natural log of 7. So let's see if you've got the idea for a couple of those. Let's see if you can choose your answer here in Edpuzzle, and I'll be right back with you. The derivative of e to the x is e to the x, and the derivative of 5 to the x was 5 to the x times natural log of 5. So hopefully you chose choice C. All right, a term we haven't really used yet is critical number. C is called a critical number of a function if C is in the domain of f and the derivative of C is equal to 0 or is undefined. So if you were given a function, and I already did the derivative for you, so let's say the derivative of some unknown function is x minus 3 over x plus 5. The critical numbers, f prime of x is equal to 0 when x is equal to 3, so that would be a critical number. And f prime of x is undefined when x is equal to negative 5. So this function would have two critical numbers, 3 and negative 5 would be called the critical numbers of function f. So if you have to find the critical numbers, you have to find the first derivative, and then you have to say where is the first derivative equal to 0, or where is the first derivative undefined. So we'll pause and let you answer another question. So the first step here would be to find the derivative, And you will often see these fractional coefficients just to make the power rule work out nicely. 1/3 times 3 is a 1, so we'll get an x squared minus 9. And we want to say, where is that derivative equal to 0? Well, you wouldn't even have to show this difference of two squares. Hopefully, everyone in calculus would come up with 3 and -3. All right, back to some more note-taking. So we've learned all of these ideas. I just wanted to highlight the fact that these are officially calculus theorems that you are responsible now. You've discovered most of them on your own. So the increasing, decreasing tests, if f prime is greater than 0 on an interval, then f is increasing on that interval. And if f prime is less than 0, then f is decreasing. The first derivative test, this is actually the name of the theorem. The first derivative test says, suppose that c is a critical number. You just learned what that is. A critical number is where f prime is equal to 0 or where f prime is undefined. So the important things in extrema happen when the critical numbers occur. So if f prime changes from positive to negative, and you've seen this before, we've been working with diagrams, so that means that the slope of the original function f was positive, and then the slope of the original function changed to negative. So where does that happen? That happens when you go over a hill. The slopes here are positive, and the slopes here change to negative. So then f has a local maximum at C. All right, if f prime changes from negative to positive, then the original graph changed from falling to rising. So that would be here. The slopes here are negative, and then the slopes on this side change to positive. So at this C value, f would have a local minimum. So this is a graph of our original f of x. And what happens if f prime does not change signs at a value of x? And I think I meant that to be a c here. Then f has no extrema. How could that happen? Well, that could happen if you had a saddle point. That could happen if you had a multiple root. So different special cases that we'll look at. All right, our concavity tests, we've already seen this. There, we have synonyms for f double prime being greater than 0. We know that that means that f prime is increasing, so that means the slopes of f are increasing. And when the slopes of f are increasing, that means that f is concave upward. And the CU will be accepted. And if the second derivative is negative, then that means that f single prime is decreasing. That means the slopes of f are decreasing. So that means that f is concave downward. So we want to make sure that you know all of those relationships. All right, the second derivative test. Remember, this is actually the name of the theorem, the second derivative test. So this one we haven't been using yet, but it will come in handy occasionally. So it works if we're in a continuous interval. So f double prime doesn't have to be continuous everywhere, but it has to be continuous near the point that you're working on. So if f double prime is continuous, and if f single prime is equal to 0, so that means that f has a horizontal tangent. So we'll try to make sense of this for you. If f prime is equal to 0 and f double prime is greater than 0, that means that f is concave upward. So what does that tell you about f? Well, let's think about that. Let's make that diagram I had before. If this is f of x, how is it possible for the derivative to be 0? That can happen only with this horizontal tangent. So if f has a horizontal tangent and f is concave upward, do you see that the only way that can happen is if we're at a local minimum on the graph? So then f has a local min. Now it could also be a global minimum, but we know for sure it's a local at least. All right, so what if f prime is equal to 0, so a horizontal tangent, but this time f double prime is less than 0, so that means that f is concave downward. Well, how can that happen? Look at right here. This is the only way that f could have a horizontal tangent and be concave downward. The only way that can happen is if f has a local maximum. So don't spend too much time memorizing that. Think about your hills and valleys of the graph. All right, a point where f is continuous and changes concavity is an inflection point. So we don't call inflection points. If you had a discontinuous graph like this that's concave up, and then there's a jump discontinuity, and then it's concave down, there's no inflection point. Clearly it wouldn't be called an inflection point if it was not joined together at that point. All right, a continuous function has a corner if the two derivatives are different. So the limit as x approaches c from the left side, so the left-hand derivative is not equal to the right-hand derivative. So remember that these were our symbols for the left and the right-hand derivatives. So what did that mean for a corner? That meant that the two derivatives, so the left-hand derivative here is a positive number and the right-hand derivative there is a negative number. When did a cusp become a corner? Remember, we're talking about our Siegel graphs for one, and that was when we had a vertical tangent. So the derivative from one side, so perhaps the left-hand derivative could be negative infinity, and the right-hand derivative at c could be positive infinity, or vice versa. So it has to be falling on one side and rising on the other side, and both sides go to a perfectly vertical tangent. All right, the extreme value theorem is new to us, but very logical. The extreme value theorem says if f is continuous on a closed interval, and let's give the endpoints a name there. Let me see what letters I use later in the problem. It looks like we're using A and B. So on a closed interval from A to B, if it is continuous on a closed interval, so think what we're talking about. We're talking about any type of graph that is continuous from A to B, and the endpoints are closed, not open, because we could have our global max or min at the endpoints. So then f attains an, I think that doesn't have to be an and, so we could say the and if we wanted to use absolute max, f of c, and an absolute minimum, f of d, for some numbers c and d in the closed interval. They could be at the endpoints. All right. All right, I was just noticing here, I think this line is a typo. It's from the next question. It appears again later. All right, so we have another understanding check here for you with an Edpuzzle question. Why does the extreme value theorem not apply to the graph of x cubed? So think what the graph of x cubed looks like, pick your answer, and I'll be right back. The graph of x cubed, of course, rises to the right side and falls to the left side. So on all real numbers, it continues forever, so it has no global max and no global min. So what's the problem? Why doesn't EVT work? Well, it would if we gave you a limit here for the domain. If we started and stopped, then it would. So it only applies to closed intervals is our problem. All right, and we got just one more idea. Fermat's theorem. If f has a local extremum at C, and if f prime of C exists, then there's only one possibility, because local extremes can only happen at discontinuities, corners, or at smooth turning points. And if we say the derivative exists, then it can't be a discontinuity and it cannot be a corner. So the only choice left is that f prime of C must be 0. It would have a horizontal tangent. So one more check here for you to answer in Edpuzzle. Read the question before you put in your answer. So our question here tells us that f has a local maximum, not necessarily the global maximum, but right here when we have a for our x coordinate, so b is a local maximum point. Well, what's the only thing that can happen if f prime of a exists? Then it's got to be a smooth turning point, not a corner, and not a discontinuity. So the only way that we can have a local maximum where the derivative exists is if the derivative is equal to 0, choice B. And I think that will do it for now.